Hi, welcome back to part 2, arithmetic sequences, and I've got some little sequences up here, and I want you to just look at the presentation here with me for a minute and see if you can detect something similar happening in all of these little sequences. And I've got half a dozen or 5 or 6, in some cases there, entries in these. Well, I've got ... So these are infinite sequences. I'm saying, can you keep going here? Would you know how to keep going? And so I want you to have a look at each of these and see if you can see a pattern. And is the pattern the same in all of them? Let's have a go. What do you think? Let's start with this one up the top here. So 1 went to 3. I think that's a 2. Oh, look at this. Look at this. This one has a common difference of 2. Common difference of 2. We saw one like that before. And what about over here now? What do you notice? That's a 4. That's a 4. Oh, that's a common difference as well. A common difference of 4. And we should check them all, of course. I'm very remiss of me here. Let's check all of them. So it certainly looks, if we continue the pattern that is evident here, you will be adding on 4 every time. What about this one? -2 going to 1. What's that? Oh, well, we'd be adding on 3. Oops, sorry. Adding on 1. Adding on 1. Adding on 1 would be 0. Adding on 1 would be 1. And adding on 1 would be 2. So it looks like this one's got a common difference of 1. Down here then, 2 going to -1 is adding on, taking off 3. And here taking off 3, and here taking off 3, here taking off 3. So this one's got a common difference, and this difference is -3, difference between the terms. And then this one down here, that's got a negative difference as well. You take off 2, take off another 2, take off another 2. Yep, that seems to follow the pattern. D is -2. So, do you get the hang of it? These are examples of, come up the top here, arithmetic sequences up here. Arithmetic sequences where there is a common difference. So what we're looking for is a term minus the one before being a common difference. Or you could put it as an minus an take 1. So it's the second term minus the first type idea. So that's why these two here have a negative common difference. Because when you take any term and subtract the term before it, then you get a negative number. Okay, so here 18 would be a term minus the term before. You're going up in negative amounts. What you're adding on is a negative. So that's our basic definition there. A term minus the one before has to have a common difference. Now let's have a look at what Pearson's have got to say about this now. And here's their definition here. And we're looking at a recursion approach here. 7 goes to 14, goes to 21. So there's a common difference there of 7. So you could say here the first term is 7, and to get any term, it's the preceding term plus 7. A common difference of 7. And you've got to start for n greater than 1. Right, you're building up from the first term. So this is usual in sequence work because n is the term number. So you don't have a negative number of terms. So n has to always be greater than 1. It starts at the first term. And then now look, we've got 2, 11, 20. So the common difference is 9 there, going up by 9. So any term is the preceding one plus 9. Again, for n greater than 1. 48 down to 39, down to 30, etc. The difference here is what is that? Neg 9 here. It's going down by 9. So therefore any term is a preceding term, take 9. And to actually create those sequences, you must know the first term here, so that you can use the recursion idea and add a number on or take it off. So here we have our formal definition here. An arithmetic sequence is such that there's a constant d for which a term is a preceding term plus d. Or it is quite handy if you want to prove something is an arithmetic sequence, you use it the other way round. A term minus the term before equals d, which is just this expression with a n take 1 subtracted from both sides. So either of those. It's any term minus the preceding term must have a common value. Okay, so, and that d is called the common difference. It's common to all pairs of terms. The higher term, the higher number term minus the term that came before. And of course, n is an integer because n is the term number. So we're starting to build up a process, a mathematical analysis, if you like, of these sequences. Let's come down now and have a look at this idea here, the nth term of an arithmetic sequence. So now we want an explicit statement, don't we? We don't want to have to generate the terms from the one before. Can we go straight to a term? So we've already looked at this a little bit. The term, any term, is the first term plus n take 1 times the difference. Now, I've just put here a screen clipping from the IB information booklet. I think it's important that you realise this is the way it is given to you in the booklet. I mentioned in the earlier presentation they like the symbol mu. So the first term is mu1. Okay, so this is any term, this is the nth term, mu n, any term you want, and then it's n take 1 times the common difference. Okay, so that's the notation they like, so I encourage you to use that IB notation rather than the A notation up there. So we're getting an explicit statement. I think, being budding young mathematicians, we should try to prove this result. So let's have a look. We start off with a sequence is mu1, and then if it's got a common difference, if it's arithmetic, the next term will be that. Then the next term will have another d added. The next term will have another d added, and we're aiming to say if we went up to the nth term, so this is mu n, what would it look like? Okay, well, we discussed this with an actual example before. Do you remember it? We played with 6, 12, 18, 24, 30, and predicted what this term would be by adding on our common difference and by making up a formula. Do you remember? We said that the sixth term here, so let's call it mu 6, was 6 plus 5 lots of the common difference, and our common difference here was 6 every time. So here, although it's the sixth term, you are adding on only 5 lots of the common difference, and we got the right answer, 36, using that explicit go straight to the term type approach rather than recursion. So let's look at it up here in general. Can you see this is the second term? This is the third term. And this is the fourth term. Uh-oh. And yes, it's true, isn't it? The number of D's in front there, can you see it, is 1 less than the term number. So the fourth term has only had 3 D's added on. And you can see why that's going to happen, can't you? Because the first term has no D's. It's the first term. Then to get the next term, you add on D. So in the second term, you've only got 1 D. In the third term, you've got 2 D's. And in the nth term, coming up at the end here, we will have n take 1 D's. All because the first term didn't have any D's in it. So every subsequent term will have 1 less D than the term number. So that's our little derivation of this formula from the IB booklet. Let's go down and have a look at some examples of what we might do with this now. So these again are from Pearson, so have a look here. Find the nth and 50th terms of this sequence. So obviously the best way to do that is to use an explicit formula. Okay, so we know the formula for this. Now we're looking at this and saying, well, there's 9 and there's 9, a difference of 9. So we're assuming that this pattern keeps going. So it's arithmetic. Therefore the nth term is given by the first term plus n minus 1 times d. So let's find, so we've just done the nth term formula straight out the IB booklet. The 50th term, okay, mu 50 is mu 1. Mu 1 is the first term plus 49, because we want the 50th term, so 1 less lot of d added, and the difference is 9. And if you do that, then you have what do we get here? I think 443. 443. Okay, so you can read what they've got over here as well, and they've done it slightly different here, differently here, by multiplying this out into that form there. Okay, so you can do that if you want, or just substitute in, might be easier. Okay, so let's go on and have a look at another one, something else we can do here. Find the recursive and the explicit forms of the definition for the following. Calculate the value of the 25th term. So let's have a look. This is going down by 5, subtracting 5, subtracting 5. So we're going to say from those few terms, we're going to assume it's arithmetic with a difference of neg 5. So what's our recursion formula? Well, here it is here. Any term is the preceding term minus 5, and it's starting at 13. So we could keep generating the terms from 13 by subtracting 5, or using our arithmetic sequence definition, mu n is mu 1 plus n minus 1d. I'll just get this going here. So here we are. If we have a look at the coming back to mu n equals mu 1 plus n minus 1d, then you've got the first term is 13, and then plus n minus 1 by, what's d? Neg 5. So you could make up a formula here, 13, hang on, we won't put plus because it's neg 5 times n, neg 5n, neg 5 by 1 is plus 5. So it has a formula 18 take 5n. 18 take 5n. And then if you wanted to get the 25th term, you'd use this one, not this one. So mu 25 would be 18 take 5 by 25, which would be neg 107. So the new thing here is the idea that you can use this formula, or you can simplify it to this by multiplying that bracket out. So that's interesting. Let's go down, have a look at another example. Find a definition for the arithmetic sequence whose first term is 5 and fifth term is 11. So we know now that mu 1 is 5, okay, and that the fifth term is 11. So mu 5, here it is here, mu 5 is the first term plus 4 lots of d, and that has to come to 11. So if you solve that, 11 equals, first term is 5 plus 4d, rearrange here, get d is 3 over 2. So therefore, what is the formula? Well, remember the formula is mu n equals mu 1 plus n minus 1d, and we just found d, so it's 5 plus n take 1 by 3 over 2, which you could expand this again, 3 over 2n. We probably wouldn't because it's all fractions, but 3 over 2n take 3 over 2, which would be 3 over 2n, and 5 take 3 over 2 is 5 over 2. So we could do that. Well, let's see, it's not 5, hang on, not 5 over 2. So it's 5 take 3 over 2, what's that? 7 over 2. So 7 over 2. And we could do it like that. Bit untidy with fractions, but either of these two forms for the explicit general term would be okay. And so the recursion formula we could have is this one, first term, and then any term is term before plus common difference for n greater than 1. So it doesn't actually say up here, find a definition, doesn't say which one to use. So you have two. You have this idea over here of the explicit formula, and then you've always got the recursive formula here, saying start at 5 and that any term is a preceding term plus common difference of 3 over 2. I think this technique here is important, to use the general formula for the nth term to detect what's going on in any arithmetic sequence. All right, come on down. We're nearly there. We have a few problems we'll go through in a minute. Now, insert 4 arithmetic means between 3 and 7. That's interesting. Do you realise, you wouldn't have seen this before, if you have an infinite arithmetic sequence, the numbers in between here, A2, A3, etc., are called the arithmetic means between A1 and AK, for example. Can we have a look at the sequence again that we started with, this one here, and if it kept going, let's say here, why are they called arithmetic means, the terms in between? Well, take any terms from there to there. 6 plus 18 is 24. Divide by 2, the mean is in between them. Okay, so with an arithmetic sequence, we can call these entries in between arithmetic means. They're the means of other terms. So here, 4 arithmetic means between 3 and 7, we're going to take that as the first term, and there's 4 terms in between, so this will be the 6th term. But by using the word arithmetic means, it's saying that we want to create in the middle here an arithmetic sequence. An arithmetic sequence. And so if there's 4 terms in the middle, this is the first, 4 more, 5, and the last one is 6. Okay, so it suggests in this problem to do it like example 5. So let's do it together now. So here, what are we going to do? Well, we want to find the common difference and all that, so we know mu1 is 3, mu6 is 7, and mu6 will equal mu1 plus n minus 1, so that's 5d. Okay, because mu6, n minus 1d, remember the formula. The nth term is the first term plus n minus 1 times d. Let's subtract 3 from both sides. 4 equals 5d. Dividing by 5, we get d is 4/5. So let's try and generate the means in between the arithmetic sequence terms between. First one is 3, next one is just using recursion idea, common difference idea, 3 and 4/5. Adding another 4/5 will be 4 and 8/5, so it's 4 3/5. And adding another 4/5 will be 5 and 2/5. And adding another 4/5 be 6 and 1/5, and adding another 4/5, it works out to exactly 7. So we call these the terms of an arithmetic sequence in there, or arithmetic means. The IB don't use the idea of arithmetic means too much. They'd say generally write down the remaining terms of an arithmetic sequence starting at 3 and ending at 7. And you're expected to, if they say put 4 terms in there, then you would be knowing that this was mu1 and this was mu6. Okay, so we're playing around largely with this formula, and I'd like you to write it in that form as it is in the IB booklet. Okay, let's go and do some problems now. So coming down, I've got your problems here for you with the formula all ready to go here with you, just remembering this is a clipping from the actual IB information booklet. So I think all of these are okay, and just go through them. We've actually just done that one, but I want you to not look back and try and reproduce it for yourself, and I think everything else there will be okay. And just go through each of them, looking back at perhaps some of the examples. Yep, that's all right. So you can pause the presentation now and have a go, and then come down with me afterwards, and let's look at the solutions. So we've got pretty much all the working out for the solutions there. That's question 1 to 4. You can freeze that and mark your work. And then 5, 6, 7, 9, 10, etc. And then through to the end. So have a go, enjoy yourself, build up your skill level. Well, we're getting a long way down the track now with these, so that's very good. But at the moment, it's cheers from me. I'll catch you in part 3.